Hello, everyone. Thank you for coming to the second session of LASS this afternoon. Today we'll be discussing forces of nature. First up, we have Michaela Intrikin, who is going to be talking about celestial architecture. So take it away, Michaela.
Hello, my name is Michaela, and I'm an anthropology major here at Oglethorpe University. This semester, I paired up with my advisor and professor, Jeffrey Collins, with my archaeology class to do research on archaeoastronomy. Essentially, this is just archaeology paired with the astronomical research and how old societies calculated and observed these phenomenon. More specifically, today I'm going to talk about celestial structure. Celestial structures and architecture is recognized through satellite imaging and thorough research. These are very large buildings, observatories that look at anything from equinoxes, solstices, calculate seasons, or even days. As you can see on your right hand, we have the Mayan calendar. Although this isn't a piece of architecture, it is an archaeoastronomy artifact. And here's another archaeological phenomenon, which is the Nazca Lines. This was actually originally thought to be an archaeoastronomy structure. However, through thorough research over decades, it was actually found that only a third of the Nazca Lines are found to be related to celestial phenomenon. So they actually struck that theory out, which just shows how through a lot of research, you can really get to the bottom of a lot of these theories and really old artifacts. So the first structure I want to talk about is the infamous Stonehenge in Britain. It actually helped define archaeoastronomy. Its signature 5 trilithons has the 2 vertical stones and 1 horizontal stone, which is, and it also makes up the 30 vertical stones, which is the Saracen circle. The stones actually originated in a city in Wales, which is approximately 40 miles away from the current structure, which is really significant considering these are whole stones that the people had to figure out a way to carry from one end of the country into a whole other country. They actually align with 12 solar alignments and 12 lunar alignments, and the hill stone, which is right over, I believe, here, it actually aligns with the summer solstice, which is the big thing as shown in this picture here that a lot of people actually gather at Stonehenge every year to view, just because it's a marvelous, marvelous view. George Hawkins actually theorized that it was probably once used as a solar eclipse calculator so that the people could really measure when each of those phenomenon would happen. Thanks to ground penetrating radar, we actually now know that underneath Stonehenge is a whole world of itself. It goes on to be an extensive burial ground, and there are even more stones underneath the earth. Second of all, we have the Giza Pyramid in Egypt, which was built around 3000 BCE. It consists of 2.3 million blocks, which is phenomenal. The bases are all aligned with cardinal directions, north and south and east and west, with a tolerance of only 5.5 arc minutes. Considering the fact that 1 arc minute is a 60th of a degree, that's extremely accurate, especially since they were building this 5,000 years ago. The pyramids were thought to be physical embodiments of sun rays from their sun god Ra, which is like really cool to think about how the Egyptians really put a lot of symbolism into their work. The air shafts inside also correlate to celestial structures, with one correlating with Orion's belt transit perfectly, and the other correlating with the star Thuban. Thuban may not seem relevant in today's sky. However, 5,000 years ago, it actually probably would have been the brightest circumpolar star, so it would have been their North Star. The third shaft today, however, it isn't explained. They're still working to see what it could be aligned with, since everything else is perfectly aligned. So I'm really interested to see what research might come about to have an explanation for that one. Next, we actually have two Mayan structures from Central America, one being the Palace of the Governor and El Castillo. The Palace of the Governor is more aligned with Venus than anything else. Its central plaza, stairway, doorway, and stela are all pointed towards the azimuth of the Venus standstill, and it actually contains more than 350 Venus hieroglyphics within the palace itself. And the carvings and numbers within the palace is actually consistent with the disappearance and reemergence of Venus in the sky. So they really did observe and measure all of her trackings and everything they could. Next up is actually my favorite building that I actually got to research, which was El Castillo, which was built only about 1,000 years ago. Its serpent-like shadow, as you can see over here, is like the head down here, and it shows a snake. You can actually only see this twice a year on the equinoxes of fall and spring, and people from all over Mexico and all over Central America go and visit to see this. And as the sun falls throughout the day, you can see it move and slither down the building. This is also reminiscent of their serpent god Quetzalcoatl, and the peaks of El Castillo actually align with Venus as well, and another solar alignment. The west plane also faces the Zenith Passage Sunway, and the stairways, there are 4 of them, equal 365 steps, which is, of course, as you know, how many days there are in a year, which, like, although a lot of this is more speculative, as if it was on purpose or on accident, the Mayans had a very advanced thought when it came to astronomical calculations. So all theories really do point to the fact that every single stone was put there intentionally. The next is the Kaaba in Mecca. This is a huge focus for every Muslim pilgrimage in Mecca. One wall faces the winter solstice and sunset, and then the other wall faces the summer solstice sunrise. And then one wall, so each of these 2 walls, one wall faces the sunrise, and then one wall faces the sunset, and then the other wall correlates with the Canopus star, all of which are very important within Islam culture. And Iraq and Egypt actually follow this same alignment, in which one wall goes straight to Mecca. Within Iraq, you have, I believe it is the east wall that goes straight to Mecca, and then Egypt, it is the west wall that goes to Mecca. That way you always can tell exactly which way to face when Muslims are praying. And lastly, we have the Tozi Observatory. This is actually the oldest, being built around 4000 BCE. The center of the 12 slots converge, and each one of these slots measures a different time. Slot 7 is actually thought to measure equinoxes, and it is believed that it is the capital of the Qing dynasty. King Yao wanted a calendar that measured not astronomical events, that so he could measure seasons, so they could have more celebrations and festivals. And with these stones and structures, archaeologists believe that it did just that. It really did measure seasons perfectly, so that the observatory workers could be able to tell the king exactly when he needed to have all of these festivals. Leslie, but why are these actually important? Celestial structures really help archaeologists and anthropologists understand culture and society. A lot of what we even build today when it comes to architecture really reflects on what our society holds important. The more skyscrapers we build, the more we value our work ethic and economy, whereas the more religious and astronomical buildings they built, the more you can understand how they wanted to get closer to their gods and how they wanted to get closer to understanding the cosmos. It also just really shows a huge intelligence of their society, especially the Mayans and the uh, Chinese, how close they got the pyramids of Giza. Everything was totally precise in the way that this was thousands of years ago, and they were able to get down to being that close to being time. Okay, and do anyone have any questions? I know that was probably very fast.
Thank you, Michaela. Yes, if you have a question, you can just go ahead and unmute your mic. And then when you finish with your question, if you'll go ahead and mute it again in preparation for our next speaker. We're going to take student questions first.
I have a question.
Okay.
Do you think that today's society, that we've made any archaeological contributions that will, I guess, leave a mark on society thousands of years from now as well?
I think everything that we do, probably since the 80s, would be very different going forward because of everything that we usually record. It's definitely going to change the way archaeologists thousands of years from now, of course, if they can use the devices, it's going to change how they see it, because they'll be able to see it's clear when it comes to movies, when it comes to literature, when it comes to cell phones. Of course, if you just were to look at structures, I think one big structure that's probably going to bewilder a few people would probably be the beam, the great silver beam that's just shaped very oddly. I couldn't imagine if we were to find that, if someone built something like that a few thousand years ago, what we would think it actually would be. And I can't tell you, I haven't done research on it, so I can't tell you what it actually does mean in our culture. But I think that would be one thing that would probably puzzle a few people.
Thank you. Other student questions? Okay, if there are no other student questions, I'm going to open it up and allow anyone to ask a question now. So again, you can unmute your mic, just call out your question, and then Michaela will answer.
Michaela, if I could, go ahead, whoever.
This is Dr. Nardo. Could you talk a little bit about how the IPM process has been valuable to you or not in your educational journey at Oglethorpe?
The IPM process has been really great for me, especially since mine is so niche. I started out wanting to do forensic anthropology, and now I've actually gotten more into cultural anthropology and archaeology. So being able to do some research on something that I wasn't initially wanting to do when I came into Oglethorpe, but now it's really piqued my curiosity, has been amazing, because I'm even more interested in such a diverse field. Archaeology is a huge, diverse field. You can do anything from ground penetrating radar, PhDs, to something like archaeoastronomy, which is really bringing physics, astronomy, and cultures and societies all together. So it's really been wonderful.
Michaela, I was really curious about your comments about new scholarship on Stonehenge, which I'm not that familiar with. You mentioned that ground penetrating radar has given rise to a lot of insights about what's happening underground. Tell me a little bit more about that. I think you sort of suggested maybe an ossuary. Just sort of curious because I'm not that familiar beyond, you know, sort of the pop culture references to Stonehenge.
Yes, I'm not super well versed in any brand new theories. While I was doing my research, I did come across recently, within the past 10 years, they started doing ground penetrating radar at Stonehenge, in which they found a huge a lot of stones up underneath the ground they didn't even know existed. They're now theorizing that on top of it being like a celestial calculator, that it's also a sort of like burial ground, or may have been sort of like somewhere that they put important people. They aren't exactly sure yet. It's just now coming out, but it's really exciting where it might go, because it's one of those things that it's in the middle of nowhere. It's these huge stones. No one really knew what they were for, you know, hundreds of years. The Romans actually tried to destroy it, so thank God they didn't. But it's something that really does piques everyone's interest, and I'm super excited to see exactly what they find when they start digging, if they do.
All right, we have time for another question if anyone has a last question for Michaela.
Is there any sort of a celestial structure that you haven't mentioned in this presentation that you're maybe thinking of doing more research into?
I have, I think these were the main ones that I could find concrete evidence of. There's a lot of them that haven't exactly been as well as researched. I still think out of all the ones that I did include and didn't include, my favorite was El Castillo, just all the symbolism when it came to the Mayan culture and the Mayan gods. They really put their all into that building. One that I didn't include, just because I couldn't find as much research as I wanted to, was, it's very hard to pronounce, but it's Teotihuacan. It actually came before the Mayans, and the Mayans took a lot of inspiration from them. It's really a lost society in terms of they don't exactly know what happened. It's a huge city. They have a lot of structures there, and there's writing, but they can't translate it really, and they were there, then they weren't there. They don't know exactly what happened to the people. So it's definitely a mystery, and I wanted to include it, but I just couldn't find enough concrete things to include it on.
Okay, thank you so much, Michaela, for coming and presenting. I think I know at least my interest has definitely piqued. I didn't know much about Stonehenge or any of these other ones, so thank you very much for sharing.
Oh, well, thank you.
All right, next up we have Jesse Storr. He's going to be talking about the biophysical forces and electrophysiology of bicep muscles. So we'll give him a minute to set up his screen.
Are you all able to see presentation? Okay, good. So yes, my name is Jesse Storr. I am overly excited to share the study that me and Dr. Bobby conducted and the kind of the data that we ended up getting from that study. So let's go ahead and jump right in. So the title of the presentation and the study that we did is Non-Invasive Investigations of the Correlates and Biophysical Forces and Electrophysiology within the Biceps brachii muscle. But before I do jump into the meat of it, I kind of want to just give a little bit of background information on, number one, why it's relevant to me, why I even chose it, and how I kind of got to do this experiment. So I am a personal trainer and a fitness instructor, and fitness in general is huge in my life. It's really important. And so at the end of last semester, I kind of started looking at exercise physiology a little bit more and was really interested in the science behind it and understanding more so what's going on physiology within the muscles and within the skeletal muscles, specifically in terms of maximizing and doing the most efficient workouts and making workout plans for my clients and things like that, and things of that nature. So I went to Dr. Bobby. I did a lot of research on EMGs, and I asked him if it was possible. He said yes, but come back next semester, because there was literally like 2 days left in the semester. When I brought it to him, I said, okay. I went back, I did my research, and we met in the beginning of the semester. And so we hashed out some things. We had a couple good meetings, and we landed on one thing that we were both really curious about. And we wanted to know, was there a way that we could basically map what was going on within the muscle, with like about, muscle activity within the muscle, or electrical activity within the muscle, and then what was going on with the corresponding force to actually contract the muscle. And so that's literally what we landed on. So before we get into the experiment itself, I do want to give a little bit of background information on electromyographies. We're going to talk a little bit about the biomechanics related to the experiment, and then we're going to go ahead and dive into the experiment. We'll talk about the results and a couple limitations, and then we'll wrap it up with some take-home points. So first, what does an EMG record? So an EMG, or electromyography, basically is a electrodiagnostic tool that is used to record electrical activity within a certain skeletal muscle. And so it's useful in many ways. There's medical diagnostics that can be used for it. And so if you take a group of normal patients and you compare the EMG readings with those of patients who may have some type of muscle disorder, it's used to actually categorize what's going on with specifically within those patients who may have those disorders. And so what happens basically, let's say for dystonia, for instance, dystonia is a muscle disorder where there's basically involuntary contraction of the muscles. And so if you look at a normal patient and you look at the EMG recordings of this normal patient, and then you compare with an EMGs of a person with dystonia or who may have dystonia and needs help being diagnosed, then you would be looking at prolonged contractions, because you know that the muscle is contracting more than it needs to be. Same thing with ataxia, which is basically opposite. Ataxia deals with those who have a disorder where they have a lack of voluntary contraction. And so again, if you look at someone who has normal muscle function, and you look at those EMG recordings, and then you compare them with a person who has ataxia, you know, if you're going to be diagnosing someone with ataxia, that one of the things you're looking for is a decrease in the amount of electrical activity that the EMG is actually recording. So it's very useful in terms of just understanding kind of what's going on within the muscle as well, and the efficiency of the muscle response. Another thing that we can use EMGs for is prosthetics. And prosthetics, the way they do this is you can hook an EMG up to the forearm muscles or the finger muscles even, and there's videos out there that you can see, but the EMG recordings associated with your own actual human arm can be used actually to move some of these prosthetics. And so it's being advanced a little bit more too, in terms of actually using it to more efficiently have people who do need these prosthetic limbs, because certain limbs that have to be amputated or things like that, whether it's accidents or just birth disorders or things like that. But it's very useful for that as well. You can look at the biomechanics of it as well, and that's just understanding how the mind actually communicates with the body and with the muscles. And so there was a really good study done with this, very thorough, where they basically looked at what was going on neurologically. So they looked at the basal ganglia in specific, and they hooked up the EMGs to a specific muscle group as well. And they saw simultaneous levels of what was going on between the brain sending that information out and the efficiency of the muscle contraction by looking at the EMG recordings. And so it's very useful for that as well. And then exercise physiology, which is where my interests lie, and where this study basically takes place. Specifically, it can be used for a number of things as well. A prime example is just understanding the most efficient way to do certain exercises, maybe the most efficient way to lift, or in order to get the most muscle activation, or to get bigger or get stronger. And so there's even sport-specific cases where you have an athlete, like a good example of this, or a really interesting example of this that I saw, is that for instance, Olympic archers, when they're looking at these athletes and they're doing certain training in order to actually get better and improve, it helps them to actually be able to visualize what's going on in terms of, can I see the minimal EMG activity? Is there as little EMG or electrical noise within the muscle going on when I'm getting ready to shoot, versus, maybe there being a little bit more than what you want. And so what they just do there is they basically want to be as still as possible before they actually shoot, or before they let the arrow go, or let the bow go for the arrow to fly. And so they want to look and they want to maintain this as still as they can, this kind of level of stillness before they actually shoot. So there are a lot of interesting and useful ways that EMGs can be utilized. But the focus of the study that I ended up doing, in the experiment that we did, was actually the biceps brachii muscle. And so within the biceps brachii muscle, we're going to be dealing with the anatomy and the physics related to it, and how that's going to, number one, give us these EMG recordings, and then give us that force correlate that we're actually looking at as well. So the biceps brachii muscle is an anterior muscle of the arm. It's a two-headed muscle. The inner bicep is the short head of the bicep, and then the outer bicep is the long head. And the main physics that was involved in terms of the calculations and deriving numbers actually for the data analysis that I did was torque. And so torque is just take an arm, which is going to be the length of the arm. We're going to multiply that by the force that we do get with the force transducer, which we're going to talk about in a second. And then you're going to multiply that by the sine of the angle that the arm is actually making, right? So I think that's enough background information to actually jump into the experiment and talk about what happened in the experiment, what we did, and what kind of data we got. So the methods and the way we did the experiment, it was basically two-phase or twofold. So we know that we needed to get the EMG recordings, and we know that we needed to get the force recordings as well. So what we had to do, we had to divide it up basically in the way we did that. And so we used the arm model, which is shown on the far right. And that's how we got the force recordings with the force transducer, which I'll talk about in a second. And then on the far left, that's where we use the EMG, the surface electromyographies, to actually get those EMG recordings and then get quantifiable data with that. Again, I'll talk about that in a second as well. But in addition to getting those two things, there had to be some type of variable that we could actually measure to map out what is the actual relationship between these two. So we did it two different ways. We increased the angle for one. We had 3 different angles that we looked at, and then we increased the weight at each one of those angles as well, in order to actually look at what was going on. Like I said, what's the effective mass on the EMG recordings with the electrical activity within the muscle, and what's going on, with that associated force based on mass, or if the angle has anything to do with it as well. So before we even took any data at all, we needed to come up with a system in order to provide some type of consistency within the experiment. So at the fundamental basic level, all there was for both of the methods that we used was there was a pivot point, which the elbow worked as, and then there were 3 different angles that we ended up using in order to get these isometric holds. So there's no confusion, just so I'm being really clear. We did isometric holds, and we saw what the muscle activity was like with these isometric holds, both with the human subjects and with the human arm model. And so let's just take 45 degrees, for instance. If we go at 45 degrees, we're gonna have a certain weight at 45 degrees. That's gonna be an isometric hold for, about 5 seconds, just enough time to actually get some recordings or some data back. And then we would let that go, take that recording down. You add more weight at the same angle, and then you do that again and again. So you get 4 different recordings basically, or 4 different data points for that specific angle. Then you're gonna go to 90, we went to 90, we did the same thing. We got 4 different recordings with 4 different masses increasing incrementally. And then we went to 135, we did the same thing there. We had our participants, and even with the human arm model, you hold the weight isometric hold at 135, and you're going to increase that weight incrementally, so you can get 4 total readings of that. So it was enough data to give us some aggregate data that we used, and we did a lot of analysis and things in Excel to actually look at the data. But the specific arm model we used in this study was the Pasco arm model. And so the Pasco arm model is simply a tool that is used to actually give us a force that is associated with the movement that's going on with the arm. And so as you can see, the blue, and I'll just show my cursor here, but the blue kind of piece of equipment that's on the end right here is that actual transducer. What you do is you pull back on it, and once you pull back, this arm rotates up. Now this picture specifically shows the arm rotating forward. There is a mechanism where you can keep this arm in place, and it won't actually rotate up. It'll stay right here the entire time. But so that's what we did. We secured it, and we pulled on it where it would rotate the weight up and perform the curl. And that's how we got the readings again at those 3 different angles with the increase in weights, so we could get those isometric hold readings and use that as some type of data going forward. Now, these are some raw force transducer data from just one angle specifically. And so again, just to show you a visual of how this looked, this first purple line right here was at 25 grams. So I took the recording for about a number of seconds, about 10 seconds total, and then we cut it off. We added 50 grams. We went back to that same angle. We took it again. We cut it off. We took the same angle, or we took the same measurement again for 75 and 100. And so we just increased about 25 grams for the force transducer or the arm model specifically, and that's how we got these recordings. Now, for the human arm, for the human subjects that we used, there was 9 total subjects that we used for the EMG recordings. And so with that, we needed obviously a piece of technology or an instrument, if you will, which is 80 Instruments EMG lab chart, to actually do these recordings. And so when we hooked the surface electrodes up to the bicep of all the participants, I had them do a cable curl, isometric hold with the cable curl machine. And so in doing so, we got a number of readings, which looked a lot like this right here. And so these are raw EMG data, and it is good to know, just to understand that raw EMG data itself is not statistically useful, because it does go above and below the x-axis. And so when that happens, basically, when you get an absolute value for that, it basically zeroes out at any point. So it's not really useful for any statistical analysis. Now, what is useful is an RMS, and that's what we use to do our statistical analysis. And so using an RMS, it's basically a sliding average. So if we go back and we look at any point in time, let's say like 1 to 5 milliseconds, instead of all the static, it takes all the readings from that 1 to 5 milliseconds, and it averages it here with 1 peak. So let's say it gives us this peak right here, right? And so the higher the frequency with the RMS, the more peaks you're going to get, the more defined they're going to be. And so that's what we use for me. The lower the frequency, the smoother it'll be. So it's kind of up to what you kind of want to do with it. But for me, having higher frequency and having more peaks was very beneficial, because I needed enough data to actually do something with. So what I went and I did, and you take 10 pounds, for instance, I went in each peak, I put the cursor over the peak, I got that response in millivolts, and I put it in Excel, went to the next peak, got the next reading right here, put it in Excel, got this one, this one, this one. And so I just averaged all these peaks up, and that was my 10-pound average for that specific person at that specific angle. So there's a lot of data to go through, a lot of number crunching, but I did the same thing from 10, 15, 20, 25. I took averages for all those peaks, or I took all those peaks down, took the average, and that was that specific response for that specific person at that specific angle, right? So what we were really looking at doing was taking this data, and we wanted to compare it to the data that we got from the force transducer. And so that's what this looks like here. And let me be really specific. This is, again, I told you we wanted to know the effective mass on torque and average RMS. So again, the torque exerted using the apparatus graph is on the left, and the human subject is on the right. And that's just the average RMS again, and that's the electrical activity that we were finding in the muscle. So this is just on mass specifically. Now, I divided these graphs up with 45, 90, and 135. 45 is the blue, 90 is the orange, and then 135 is the green. But the only thing I want you to focus on with this graph is the trend that we see in both of these. Now, with increase in mass, no matter what angle you're at, you're going to get an increase in the amount, either the torque needed to actually move the weight up, or the amount of electrical activity within the human subject. So that is the trend we're seeing in terms of corresponding data and looking at how it's correlated when we look at the electrical activity within the human subjects and the torque from the apparatus that we used. So when we did that, we saw that, okay, there's a positive trend between both the apparatus and the human subject. So that's just on mass. Now, when we look at the effective angle on torque and average RMS, this is when it gets a little more interesting. So it is good to note that with torque, at least, you're going to get the max. You're going to get the max torque basically at 90 degrees. That's just a characteristic of torque. So we got what we were looking for in terms of the torque that we were looking at for the apparatus. It peaks at 90 and then it drops all the way back down to at 135. And looking at just how angle plays a part in this. I mean, even if you look at the human subjects, it's not exactly the same in terms of the exact visual that you see where it goes up and comes back down, but it does start high and then comes off back low. So generally, we can make the conclusion, and we can make the observation to say that in general there is a clear pattern here. Even when looking at the effective angle on torque and average RMS, it may not be as drastic as with the apparatus, but again, the apparatus is just a model. So it's just there to try to give us some type of reference when we're also doing the human subjects. And that's what we were trying to do here. We were just trying to use a reference to see if we could actually correlate what we were getting within the muscle electrically and the force or the torque that was actually being exerted by the bicep with the apparatus. And so in doing so, again, we see that there's exact same thing going on here. And basically the reason why we see this, and some people may be like, well, why does it peak at 90 and then come back down, or why in the human subjects even does it have like kind of this downward trend? That's because of just literally the biomechanics of doing a bicep curl. So you're going to get most of your you're going to get most of your resistance or muscle activation from the 45-degree angle, or at least all the way up to the 90-degree angle. Once you get past 90 degrees, what happens is the forearm itself and then the elbow start supporting the weight a little bit, and the bicep doesn't have to work as hard. So especially when we're at 135, and that's why you see that this huge drop off right here in the apparatus, especially when we're just talking about torque. I mean, even when you talk about human subjects, it drops off as well. It's not as drastic again, but that's why you see that drop off, because the bicep does not have to support the weight as much, just because the weight is now coming straight down basically on the elbow, being supported by both the forearm and the elbow. So that's why that happens. Now, we looked at the correlation between the two with the mass and the angle and the effect on the torque and the RMS. So now let's look at how can we actually make some conclusions based on this data. So since we're just talking about angle, I think I just rather just stick with angle right now since we're right here. And when we look at the angle dependent summary figure, we see on the left, let's just focus on the apparatus at first. We see one major thing, or technically two things. The first thing is that the difference between the 45 and the 90-degree angle, which are represented here and here, they are not significantly different in terms of the torque needed to actually move that weight. And we see that by the overlap in the error bars right here. Now, the 135 angle, for instance, though, now we see that that is very significantly different than the activation, or at least not the activation, the torque you're going to get using the apparatus. And again, this is just using the apparatus, so it is limited in terms of application, but this is what the data is telling us, that at least in terms of torque, once you go past 90 degrees, there is going to be a drop off, and there is going to be some type of significance in the difference, at least if you go all the way to 135. But if you're just talking about torque, again, going from 45 to 90, there's not going to be much of a difference in terms of just torque alone. Now, if we look at the human subjects, it paints a different story, and we see that there's no significant difference at all for either 45, 90, or 135 across the board for those angles. Instead, they're all within each other to basically say that you're going to get as much muscle activation, at least using the cable curl that was used and using an isometric hold, that you're going to get at each one of these angles. It's not like you're going to peak at 90, or it's not like there's going to be, although it's slightly higher, it's not significantly different. So it's not really worth kind of noting, or at least changing and making a workout plan or changing a type of exercise variation specifically for angle based on this data, at least that we got here. Now, if we look at mass, however, mass is basically the flopped concept. And there's a couple reasons for that. But if we look at the apparatus first, which is on the left, we see that, again, the error bars here, just like we saw with at least the human subjects over here. Most of the error bars overlap. Really, all of them overlap. The only ones that don't overlap is this 25 right here and this 100. So what that tells us is, at least for torque, unless we take that weight from 25 grams all the way up to 100 grams, there's not going to be a significant amount of difference in terms of muscle activation. So even something like, I mean, it's the 25 is barely missing the 75 as well. So even in saying there, like, you got to at least increase about 50 grams in order to see any type of like statistical significance with the difference. With the human subjects, however, though, when you're looking at muscle activation and electrical activity within the muscle, we see that once we increase mass, there is at every single point, whether it's at 10 pounds going to 15 or 15 going to 20 or 20 going to 25, it's statistically significant increase in the weight every single time in terms of in terms of electrical activity. And so this isn't changing the angle. This is weight specific. So let's just say we're at 90 degrees. If I put 10 pounds on at 90 degrees, that's my reading. I know for sure and this is what this data is telling us, that I know for sure I'm going to get more muscle activation. I mean, just look how tight the error bars are even for these. Like, you're going to get more muscle activation. You go from 10 to 15, 15 to 20, 20 to 25. And so what this data is really telling us is that, at least for muscle activation, it's not really about the angle that we're doing the isometric holds at. It's about the weight. It's about progressive overload. So there's really two different ways you can do progressive overload. You can either increase the reps, which we didn't talk about here because we're just doing isometric holds, but it's worth noting. And then you can increase the weight, which is exactly what we were talking about here. And so that just seems to be, in terms of muscle activation and damaging the muscle and repairing it and getting stronger, and actually just making those muscle fibers work harder and recruit more muscle fibers. That's what the data is telling us, that you do need to increase the mass, and don't worry so much about the angle, at least using a cable machine, But before I wrap everything up, I do want to talk about a couple limitations within the study. I know there are like a lot on here, but so first, the apparatus, there was a force max. And if we go back real quick to the weight right here, so there was a force max. And what I wanted to do at first was do 50-pound increments. But once you got a little bit past 100 grams, it basically just maxed out and it wouldn't give you any higher of a reading. So I had to scale it all the way back to 25-gram increments and starting at 25. So what I know would have happened, and just seeing it here with the 25 not even overlapping with the 75 grams, and you can see that right here and then right here, what I know would have happened if there was a bigger difference in terms of the increment, the increments that we were increasing the weight by with the force transducer and the human arm model, at least, that everything would have been in line, at least even with the human subject stuff about everything being statistically significant, but there has to be enough of a progressive overload. So that's even going back to the human subjects. If I would have maybe just increased it by 1 pound, then we know, okay, well, there might be some type of, there might be a little more muscle activation, but it's not going to be significant, really, most likely. Now, increasing by 5 pounds is moderate, but again, it's enough to make sure that there's going to be a significant difference in the amount of muscle fibers being recruited every single time at those specific weights. So that's one. The range of motion, I originally wanted to go all the way up to 180 just to see that type of recording, or what kind of data we got from there, and see how that panned out. But again, the force apparatus, or the human arm model, only went so far, and so we had to cut it off basically at 135. And so that's why we mapped the EMG to do the same thing. I said, well, let's just make everything straight, the same across the board. So that was one thing. There's a couple mechanical irregularities. Well, one main one, which there was a hitch. There was a slight hitch in the arm once you were pulling down on the transducer. Once you got a little bit past 90, it kind of stuck a little bit, and there was a little bit of a hitch, and then it came up. And so it just wasn't exactly perfect in terms of modeling an actual human arm. And then just universal application in general. It was pretty specific to the study that we did using the apparatus, unless we changed the angle up a little bit or changed the arrangement or the way we actually set up the human arm model when we were taking the experiments. Again, it is pretty slim in terms of how much application there is in terms of other fields, and even doing the same thing but doing it various other ways. And so you'll see that even in EMG. But first, I want to talk about the possibility of non-intended electrical noise for EMG limitation. There's always a possibility to have a little bit just a little bit of extra noise that you kind of don't want there. Number one, you can get it from just the electrical activity within the room. And what I mean by that is just the wires in the room or the building you're in. It could be anything simple as that, to the adjacent muscles making any type of electrical noise when you're using surface electromyographies, because the surface electromyographies are literally just electrodes, just flat electrodes that you just place on top of the skin. And so sometimes they're not super accurate and they might pick up some adjacent muscle noise. But again, we've always run a ground to the hand that runs that extra noise there to try to get as fine of a recording as we can. So on top of that, the precision of angle, position, when I was doing the recordings for the human participants, I was being as careful as I could to be as precise as possible. But again, there was probably, and that's why we see the error bars are a little bit larger for the human subjects, depending on angle. But there was probably a little bit of wiggle room there in terms of like actual precision or accuracy there. And then sensitivity of arrangement really ties in with universal application. But basically, we did this experiment a specific way, and we had the participants stand very close to the actual weight that was being basically pulled down on them. And so what I saw when I was going through the data, I was like, okay, well, if this is what we're getting, doing it this way, well, if we do it a slightly different way, what will that kind of be like? What kind of recordings will we get? And so I didn't include it in the presentation just because it was something I was interested about, but I got 5 more participants to come along and help me out. And I had them take 2-3 steps back from the actual cable. And so now instead of the cable pulling straight down, it was pulling down and out. Right. And so now there's an angle here that we got to consider between the elbow and the bottom of the cable. And so that makes it a lot more complicated and interesting in terms of, okay, well, how much more does angle affect, the torque even needed there, or the muscle activation needed there? Because now the elbow and the forearm aren't really a part of the equation, because the force is now going out. So the biceps still having to work a little bit harder. So that was one thing to consider as well. And then, excuse me, when we look at correlation, I know I talked about the kind of simultaneous recording between the basal ganglia and the muscles of interest. That's one type of simultaneous recording. I've also seen simultaneous recordings within, more than one muscle to see if there's any co-activation. Again, going back to the medical diagnostic. And then I've also seen stuff with video kinematics and muscle activation using EMGs and using actual video camera to see what's going on visually at the same exact time that you have, with the EMGs. So if we could have figured out a way to actually get the EMG recordings and look at the electrical activity within the muscle and get the force readings, then it would have obviously been ideal if we could have did that at the same time, literally within the human subjects instead of using a model. But, I think we did best with what we had access to. Second thing, compatibility. The human arm model just wasn't the perfect model to map the human arm, just because, again, it is just a piece of metal equipment, and the elasticity of actual human muscle, human skeletal muscle, is just something that hard to be replicated within a model. But again, it gave us enough information for what we needed. But again, to be optimal, and just one thing that probably limited it a little bit in terms of the data we got was just the actual compatibility between the actual human arm and then the model. And then last thing, sample and sample size. Sample, what I mean by that is that greater athletes will need less muscle fiber recruitment in order to do the same exercise that maybe someone who doesn't lift as much would need. And so you're going to get, let's just say we're at 10 pounds and we're at 90 degrees. If I have a really good athlete, they're going to give me a lot less recording on terms of, or a lot less noise on the EMG recording, because they need a lot less muscle fibers to actually work to make that happen, in terms of somebody who maybe doesn't lift at all and I ask them to do it. And they're going to give me a lot more noise. So just being a little bit more consistent in the sample size might have given me some more significant data. But again, because something that we can improve, something that can be improved on going forward. And then sample size, I did have 9 participants for the human arm model. I had 14 in total, but I didn't include the extra 5, obviously. So I think 9 is a pretty good size, but I think I could have got some more and made the data a little bit more significant. But again, that's just one thing to think about going forward. So some take-home points real quick to wrap it up. Number 1, what is an EMG? An EMG is a tool used to evaluate and record the electrical activity produced by skeletal muscles. Okay, and this is what was used within the human subjects, again, in order to get that electrical activity or muscle activation within the skeletal muscles. Now, RMS, if you remember, raw EMG is not useful because you cannot really do any type of analysis for it using a raw EMG, because it basically gives you an absolute value of 0. But an RMS is useful because it produces useful quantifiable data for analysis, right? Also, one thing to kind of just wrap up the whole point of the talk, or not the talk, the experiment, excuse me, is that there is a correlation between the amount of muscle response, which is the electrical activity within the muscle gotten from the EMG, and then the torque needed to curl given weight, which was gotten from the force apparatus. And so that's what we saw with the data. And then the last thing, and again, this is just what the data told us, at least in terms of the muscle activation, being able to, that we mapped with the EMG, excuse me, and that is that progressive overload is the most effective method in eliciting higher muscle activation on contraction. So progressively increasing the weight is going to progressively give you more muscle activation, progressively recruit more muscle fibers, and therefore giving you a larger response. So few acknowledgements real quick. Dr. Charles Bobby, professor of biology, has been great the entire semester about helping me with this, and just really had my back with a lot of stuff in the beginning. And it was a real pleasure working with him. Professor Daniel Howard, again, one of the most passionate people I know at Oglethorpe, and he gave me a lot of the help in the biomechanics of everything, and kind of mapping the physics into it, and doing those calculations and things like that. And then just all the participants that helped me out and volunteered themselves to let me experiment on them. I really appreciate them as well. So that is all from me. I can take questions now if anybody has them.
Yes, thank you, Jesse. So now we're going to open up the questions first to students, get some good student questions before we open up to the whole audience.
I have a question. First, Jesse, great job. Awesome.
Thank you.
Really enjoy that. I guess one of my questions that was going to be at the beginning is, what's the most efficient way to do like a bicep curl now, right? Because in a way you're measuring kind of like EMG and the force and all those things, using an EMG and all that stuff. So given that you saw that the electrical activity is kind of like the same throughout, it's kind of, I guess, it doesn't matter whether you do the bicep curl and stop at 90 to be more efficient. It's just kind of rep them out in a sense.
I mean, so when you're looking at the angle by itself, like we saw, and I'll go back to the figure real quick. So when we're looking at the angle by itself, there is no significant difference in the angle. So you're right, and it is more so about progressive overload in terms of the data that we did get. That was kind of opposing to my own belief at first, because I did understand the way free were, and they did use a cable, and so that's why I said, just even having the participants take a couple steps back, when I added that in there, I saw that there was a slight difference in terms of activation within the bicep. Even at 135, I was getting basically like more activation within the bicep at 135, and I just increased that angle by taking a step back. So I think it depends on what you're using. If you're just using free weights like a dumbbell, then I'd say you're still probably going to get your peak contraction at 90 most likely, but using a cable is a little bit different. And I think just the slight variation of using a cable, even though it almost acted as a free weight because it was kind of stacked, might have given not a significant difference or a significant data in terms of the difference between the few angles. But again, I mean, I think it's still important to still factor into what we got from the torque. And so from the torque, at least, we saw that there was a big significant difference between 45 to 90 and 135, which is the theoretical kind of relationship we're looking for. So I think it depends on, number one, like what you're actually using. If you're using a dumbbell like a free weight, or if you're using a cable, and then if you're using a cable, how close are you to the actual weight? Is it like pulling right down on your arm, or are you taking a few steps back out where it's actually pulling out and down now? And so it's increasing that tension on the bicep as well. So it's kind of multifaceted, but I mean, I still think it's really interesting in terms of furthering the study, and maybe and actually carrying on what I did when I had to just step back and then actually comparing the data. Because when I did the little analysis that I did, like kind of the micro analysis that I did, I saw that there was a difference, and there was actually more muscle activation even at 135, and it didn't drop back off. So it's interesting stuff, but that's a good question.
Thank you. Jesse, would you mind muting and then unmuting your mic? We were getting a little bit of reverb there, and I think that might help. Okay. So thank you for that question, Jose, and thank you, Jesse. Are there any more student questions? We'd love to hear from students.
I have one.
What other like sources did you draw from? Like besides, is it just like a totally independent study, or were you like inspired by anything else?
Yeah, I mean, there was a number of studies even that I mentioned in the talk that I had read and that I had got some inspiration from in terms of what I wanted to do or how I was going to kind of do the experiment. But in terms of what we did here, it was completely independent with mapping the force related to the actual electrical activity within the muscle. So doing that and comparing the model to the human subjects was completely me and Dr. Bobby came up with that. But I did read a number of things that kind of I mentioned as well on how they were doing this kind of dual analysis and trying to see what was going on in one part of the body and or seeing the relationship between the skeletal muscle with maybe other areas of the body. So yeah, but it was basically independent.
Okay, I think we had another question as well.
Yeah. So do you think using a dumbbell would have changed the results instead of using a cable?
Yeah, I personally do. Just kind of talking about how close I had the participants. I mean, it wasn't perfectly over the cable where it was pulling straight down, but again, it was basically like that. But I still think you would see somewhat of a different result. I don't know how different it would be, just because the cable acted so much like a free weight in terms of just looking at the biomechanics of it. But I do think in general that we would see slightly different results. But again, if I would have taken everybody from the get-go and had them take a couple steps back and created that extra angle between the bottom of the cable and the elbow or even the point where the weight was in the hand, and then you compare that with free weights like a dumbbell, then for sure it would be significantly different. But depending on, or considering the way I set up the experiment, then I don't think it would be too much different, but I think you might see a little bit of difference with a dumbbell with the cable and the way we did it.
So do you think, I'm sorry. So do you think using the cable would be more effective in terms of building muscle mass or a free weight?
Again, it just kind of depends on how you're lifting, because if you take those couple steps back, if you're really trying to maximize, like, because the peak of the bicep contraction isn't at 90 degrees if you're like flexing, at least if you're just contracting the muscle, it's not at 90 degrees. It is when you're all the way up at 135, like you want to have that peak contraction. And so even with something like a resistance band, like the more you stretch a resistance band, the more resistance you're going to get. So the more you're going to actually stimulate the muscle. So with the cable, if you're using a cable and you want to actually get that peak contraction at the peak of kind of that contraction or if you want to get peak resistance with the peak of contraction, then you're going to want to take those few steps back and create that angle instead of being right up on the cable, which will act more like a free weight. Because like I said, again, that free weight kind of relationship is that once you get past 90, or if you get all the way up here to 135 or 180 even, the bicep isn't working that hard up here, not with the regular free weight. But if you add that extra factor with adding that angle by actually stepping a bit out, and then you have the cable pulling out and down instead of straight down, then that's going to make it a little bit harder as well. So it kind of just depends how you're doing it. But if you were to want to choose a cable curl over a free weight or like a dumbbell, then taking those few steps out would definitely be beneficial. But otherwise, then there's not really much of a difference. Not the data at least doesn't show that there is.
Okay, at this time, I'm going to open up questions to everyone in the audience. So if you have any questions, please ask.
Jesse and Michaela, good job. This is Dr. Nardo. I had a question for Jesse. Did you do any sort of analysis of the physics-based mathematical model and whether your empirical results were consistent with what that mathematical model would say?
I didn't. I was going to at first, and then because I kind of had to change the way I approached it at first, because when I noticed, at least initially with the cable, I didn't even look at it as being almost acting like a free weight until I actually looked at the data I was getting. And so that's when I said, okay, well, let me get some more participants and see if I have them take a couple steps back, like, is that extra angle actually going to make a difference? And it actually did. And so initially I was trying to figure out all the physics for that and trying to figure that out. I was with Dr. Howard, just grinding it out. And then I went back and I looked at the data again. And I said, you know what, it's enough in terms of like, okay, we expected a different result with the cable at first, but it's still consistent enough, at least because they were so close and acted like a free weight, to just go ahead and compare it just flat out and just compare it with the apparatus that we got, the data we got with the torque from the apparatus, and then the electrical activity within the muscle with the human. So I didn't do any further type of comparison, even with the apparatus alone. I just took the raw apparatus data after grinding it down and getting that analysis done, and then compared it with the analysis I did with the EMG. And so, like I said, across the board, they did correlate, and they did have basically the same pattern. And so that's really all I was looking for here, was just verify that they had the same pattern.
Other questions from the audience? Okay, if there are no other questions, please join me in thanking Michaela and Jesse. We really appreciate you guys coming and talking to us about your research.
Thank you.
Thank you. Bye-bye.
All right, bye.